All right, so down here, we can take a look at the syllabus. Here. So today I'm just going to go through a quick intro, and then we're going to review chemical properties. But we're going to primarily focus on chemical properties this semester. And so I want to just go and get everybody thinking in the same, at least the types of chemical properties in the same, I guess, jargon. So, intro and then chemical properties. What I mean by that is there are lots of ways to divide up chemical properties. I like to classify chemical properties into three groups. And the three groups are based on the driving force for the reaction. And so the three types of chemical reactions that we'll be looking at today are metathesis. Metathesis are like your basic double replacement style reaction. There are others. Acid base. There's some overlap here. Some acid base reactions are metathesis, but many aren't. Can't be classified, so that's why I have a whole another category. And redox. It could be oxidation and reduction reactions. And so that's what we're going to be doing here. In Chem 1A, what we looked at were like the qualitative driving force. Like, you know, if there was a driving force present, we'd expect the reaction to occur. If there were no driving force present, we'd predict no reaction. In Chem 1B, what we're going to spend a lot of time doing is quantifying the driving force. You know, how strong is the driving force for reaction? So, in fact, when we look at that, you know, for some reactions, there's a strong driving force. You expect the reaction to go 100%. But for other reactions, the driving force isn't so strong. And so what happens in those cases is that the reaction doesn't go 100%. You know, sometimes the reaction only goes like 60%, or even 1%, or even less than 1%, depending on that. And so we're going to spend the first 5 chapters dealing with that. In chapter 16, well, actually, not the first 5 because we covered chapter 24 up front, but 16, 17, 18, and 19 all deal with that. You know, to what extent do we expect? You know, is it 100% reaction or 60% reaction, or what is it? So the first 5 chapters, 16, the first main 5 chapters, 16, 17, 18, 19, 16, 17, 18, 19, and 20, actually. 20 is looking at redox reactions. We'll talk about that in a minute. Maybe most of them more. This 13 is thermodynamics. Thermodynamics, we're going to put numbers to it. So the first, let's say, 5 chapters comes from a more of a observational, experimental approach, whereas when we get to 13, it comes from more of a theoretical approach to driving force. And then, even if we have a driving force, the reaction might be very slow or it might be very quick, you know, like explosively quick. And so we're going to look at that, chemical kinetics. Because really to understand chemical properties, we want to know, is there a driving force present? How strong is that driving force? And how fast do we predict the reaction to occur? You know, is it going to be very fast, do we expect, or quite slow? You know, some reactions are exceedingly slow. And it's almost as if no reaction should take place. Common example of that would be like diamond. You know, diamond is thermodynamically unstable. compared to graphite. Graphite's more stable, so it should be downhill in terms of energy, but diamond's what we call metastable. You know, it's going to take forever for it to decompose into graphite. And so that's why we think of diamonds as being forever, even though there is a driving force to convert it to graphite. And so kinetics, and then, which is chapter 15. So we're bouncing around some chapters. And then we're going to go to redox, which is chapter 20. And then chapter 24, which is the second half of chapter 24, essentially. Chapter 24 deals with Lewis acid-base reactions and a specific application of Lewis acid-base reactions, which are metal complexes. We'll look at that later. And then we're going to end the semester with chapter 25, which is nuclear chemistry. Nuclear chemistry follows a different set of rules than regular chemistry. For most of the chemistry, even these chemical properties, when we think about like fundamental forces of nature, what fundamental force of nature is most important to chemists? If you think like physics stuff, like you'd have gravity. What other forces of nature are there?
Maybe temperature?
Well, temperature, temperature, when we think of temperature, we just think of, what do we think of in terms of temperature? What is temperature a measure of?
Energy.
Energy. What type of energy are we looking at? Normally when we think of energy, we think of two types of energy. What are the two types of energy? Potential and kinetic. So temperature would be a direct measure of kinetic energy, motion. And definitely temperature can cause things to occur, but normally when I think about fundamental forces of nature, gravity is one, and then electricity and magnetism is another, and then nuclear force is another. And so in chemistry, we look at electrical forces, but there are forces stronger than electrical forces, and that would be nuclear forces. And nuclear forces are what's important. In fact, electrical forces are negligible in nuclear reactions, such that nuclear chemists typically don't pay attention to electrical forces. Whereas for chemistry, that's all we pay attention to. And we never in chemistry mess with the nucleus. The nucleus is held together by nuclear forces, which are way too strong to interact in chemical processes. So we're going to end the semester with chapter 25 here. Now, the way it's going to work is I'm going to give, rather than midterm exams, I'm going to give chapter exams. And so we'll do something like this. We'll have quizzes interspersed here, but just as an example, let's say we finish, this I'll give you more time to review here, but let's say we finish chapter 24, then the following week we'd expect an exam on that. Or if we finish chapter 16 here, then we'd expect an exam the following week on chapter 16. So I don't have the dates in there because the syllabus is just what I like to follow, but sometimes I fall behind. Well, usually I fall behind. And so that changes the dates a little bit. All right, Monday and Wednesdays are lab days. We aren't going to start lab until next week with just safety and check-in here. Our first lab will be on the third week here, the Chaplier's principle. So for this lab, you'll need safety goggles and appropriate dress, closed-toe shoes, etc. We'll talk about that here. So our labs are going to be on Monday, Wednesdays, and some of these labs are single day, others are multi-day. And so this is a pretty short experiment. Same with this lab here, hydrolysis of salt. Now the labs, we used to have a lab manual, but it went out of print. And so the labs I'm going to post on Canvas. And so you'll just download it off Canvas. This will be an example of a multi-day lab here. We're going to do synthesis of transmission metal complex. And that synthesis over 2 days. Actually, it's going to be over 3 days. On the third day, we're going to weigh our product, what we synthesize, and then we'll start the pH titration, day 1. We'll go to here, day 2. We're also going to have some computer lab days. And so here, data refinement just means working up the data. So at Chem 108 computer lab, we're going to take our titration data and graph it, basically. And then over here, we'll use the computer data to try to determine what our unknown acid is. For some of these labs, these are just going to be a simple lab report. Like, for example, Le Chatelier's and hydrolysis of salts is a very short lab report. For others, I'm going to expect a formal scientific report like this, transition metal complex synthesis. We'll write a full scientific report for that. And we'll go through this first one together here so you know what to expect. And so pH titration is also going to be a formal write-up. Qualitative analysis is going to take a number of days here, quite a few days. This one's going to be a simple write-up. It's not a formal write-up. But it's going to be worth more points since we have so much time invested in this. On April 10th, actually, I'm going to be absent on this day, April 10th. So what I'm going to do is I'm just going to post a lecture for this. So just make a note of that. There's going to be no class on April 10th. But there'll be a lecture, so you'll be required to watch that. And then we have spring break after that. We'll be finishing up qualitative analysis here. This was a computer lab here, Visual MinTech. That's a free computer program that we're going to use. Then we have something called the rate law, and so we'll have some rate law determination labs. And then some more computer data analysis here. And then can you make like an asterisk here, note on, there is a chance I might have to be absent on May 14th, 15th, and 19th. I'm not sure yet, but if I have to go, then I'll be posting. Since this is computer data workup, you can do this in other computer labs as well. And so I kind of left it open lab. Okay, and then this kinetics lab, which is how fast reactions occur, rate law, kinetics, that would be a formal report too. And then we have electrochemistry. This is not a formal report. This will be over 2 days. Here. This is redox. And that's pretty much it for the labs. Oh no, one more lab. Molecular models. We'll be building models. That will be for chapter 24, part 2. Oops. This syllabus, sorry, I uploaded the wrong syllabus. Actually, did I not correct this one? 1242. You know, it's kind of weird. but maybe, I thought maybe it's beneficial here. Go back. Check if I fixed it here. No, it didn't. Yeah, I'm sorry about this. I looked at the calendar again and I realized I made a mistake. Normally I think it's 16 weeks, but we have 17 weeks. 18 if you count spring break. And the reason is because we have, you know what the final day of the semester is? It's not June 12th. June 12th, and then we have graduation on June 13th. And then the weekend, 14th and 15th. The last day of the semester is Monday, June 16th. You aware of that? All right, so I redid the syllabus, and for some reason I didn't, but the only change was I extended some of this out here and then put this. Monday is a lab day, and so what I did was final exam part 1, it would be like multiple choice. That I moved to Monday here, June 16th. And then this was only an hour and 25 minutes on June 12th. And so this would just be like free response type questions here. So I broke the final up into 2 parts, like I did in Chem 1A. Yeah, Chem 1A. All right, so I need to post, I'll correct this. I'm gonna repost the syllabus. It's on this computer here, so I can't show you it. Here. All right, any questions on this? All right, here's a catalog course description and our course objective. SLOs. All right, so the required materials, we're using the 12th edition again, but if you have an earlier edition, that should work without a problem. The 12th edition is the latest edition. And then I'm going to use Mastering Chemistry. Was that useful last semester? Okay. We're going to continue with Mastering Chemistry then. If you have your comp notebook from Chem 1A, you can just use it for Chem 1B. You should have plenty of pages left. But if you don't have one, if you could get a quad ruled with some binding. If they're out of quad ruled, they had a lot of quad ruled in the bookstore. Like if you walk in the bookstore and then I think it's in the arts and engineering section, there are a whole bunch of composition notebooks, and on the far right, they had a stack about this high of the quad ruled ones in the bookstore. Safety goggles from Chem 1A are fine. Scientific calculator. If you could get a scientific calculator that has an equation solver, like quadratic equation solver, that'll save you a lot of time on homework and the exams as well. That way you don't have to do the quadratic by hand. And so this would be a non-programmable scientific calculator that does equation solving. And a Sharpie, we'll have some Sharpies, but if you want your own, bring it to lab. Also, a lab coat or apron is handy, and nitrile. Nitrile, in general, have better chemical resistance than latex gloves. So people prefer nitrile. Plus, nitrile gloves breathe a lot better than latex gloves, and they're stronger than latex gloves. All right, required assignments. You know, everything's required. the exams and the labs, etc. If you do miss something, sometimes there's the opportunity to make up a lab. It depends on the stock room, you know, if they have the equipment still set up or not, and the time. You know. You can make it to the afternoon session for makeup. That could work. Makeup tests are going to be more complicated, so we'll take those case by case. All right, even if you withdraw, you have to check out. Check out is mandatory, otherwise they place a hold on your transcript. And so be aware of that. All right, the point breakdown. We should have 1,000 points here, roughly. Right now it adds up to 1,000. The final exams were 20%, the labs are 18%. Homework is going to be 10%, and the rest of the exams are going to be more than 50% here. The exams and quizzes, sorry. The quizzes, I said 5 points each times 10, but that's going to vary. So, put that in there. The breakdown here is going to be 88% and above for an A, 78% for B, 65 for a C. Actually, if you fall in this region, if you take the final exam, I can give you a D regardless of where your percentage lies. One of the things, though, to pay attention to, and this is the same in Chem 1A and Chem 4, is, you know, even though the labs, 18%, theoretically, you can just skip all the labs and pass the course, right? It's only worth 18% of the grade. But at schools like UC, the lab class and the lecture class are two separate classes. Whereas here, they're combined. And so, because of that, UC requires us to fail anybody, regardless of how well they're doing in lecture, if they fail lab. And so don't skip lab. Lab's very important. Okay, note on cheating, special needs, changes. Here, you can read through this. Changes are going to be announced like either in lecture or on Canvas or Canvas. All right, any questions on this? No? All right.
So the work is on Pearson?
Yeah, the book is strange. I don't know if they have a hard copy of the book yet. Pearson's trying something new. So our bookstore actually can't purchase the book yet. And so you can't get the book. What they have at the bookstore is 11th edition. 11th edition is the previous edition. So they have the 11th edition, but we're using the 12th edition, which is, it's just close, but not quite the same. So this is what the 12th edition looks like here. Go to the cover page. You know what these are?
Is it gallium, right?
Not gallium. Gallium, this is liquid. These are liquid elements. There are only two liquid elements on the periodic table. One is bromine, is a liquid, and the other is mercury. So these are balls of mercury. Mercury hates this table. And so this is called beading. Beading, mercury just wants to minimize its contact with the table surface here and maximize its contact with other mercury atoms. So mercury just likes to be with itself. These balls make it very difficult to clean up mercury because if you hit one of these balls, then it breaks up into lots of little balls. And these balls roll around all over the floor. So you try to sweep them up. So when we have mercury spills, it becomes difficult to clean. And we still have mercury thermometers, so be careful with those mercury thermometers, because if you break them, you form lots of little balls of liquid mercury that disperse everywhere. And of course, mercury is a heavy metal, so you want to minimize your exposure to mercury as much as possible. So this is our book, and so if you get Mastering Chemistry, it should come bundled with it, and so you'll have the electronic text version of our textbook. Let's go to the home page here. I don't know if this is the same as yours, but there's a study and exam prep. Do you guys have that as well? In your version of Mastering Chem? Yeah? Okay. So you can do practice quizzes, I think, go through concepts. They also have these videos here that help illustrate the particular topics. Here. Okay, and then the homework. The homework. Study and exam prep. We go to I posted the first couple of homework sets here. Has anyone taken a look at it? Is it there, Rebecca?
I wanted to ask, do you know if what the password is we put in to log into the account?
Into your Mastering Chem account? I don't know. I mean, there's a course code, so just look for my course. And are they requiring a passcode in order to register for my class? Does anybody know it?
Like the course code?
The course code?
It's under the homework information thing you post
Okay.
in the announcements.
Text view. This is taking me to a different spot, but we'll take a look at the homework here. So you're going to come here, and this access code is if it came bundled with the book. Then you enter an access code there, but you would have had to pay for it at the bookstore. So unfortunately, you're going to have to use one of these ones here. But it's up to 24 months. So your 1A login should be fine for 1B. You don't have to you shouldn't have to do anything. You should just be able to add the course in there. Okay. This is asking me to pay. For some reason, it's not letting me get to my homework or my course. I'll check it later. But take a look. If you have any problems, talk to me tomorrow or ask me tomorrow. Or actually, there's one final thing we need to talk about. that's my office hours here. So I didn't write this in the syllabus, but maybe let me take a look. This may be subject to change here. On Mondays, it'll be after class. Our class ends at 12:40. It's our lab. So from 12:40 to 1:10 I'll have. And this is at the end of the afternoon lab class in the same room, 4:20 to 4:50. On Tuesdays, which is today, I'll just have a night one. This is kind of late, 9:30 to 10:30 p.m. So we'll see how that goes. And then on Wednesdays, it'll be after lab, after the morning lab and after the afternoon lab here. We'll stick around. Or by appointment. You know, if you can't make any of those times, let me know. All right. So I am not planning to do PowerPoint. Unless, except for this, it's first chemical properties thing. So chemistry, this is the dictionary definition. The science of the composition, structure, properties, and reactions of matter, especially of atomic and molecular systems here. And so we're going to be looking at the properties. When I think of properties, I think of two types of properties. What are the two types of properties that we deal with? Physical and chemical properties. Chemical properties are just chemical reactions. What chemical reactions does it undergo? So chemical properties and chemical reactions are the same thing, for me, interchangeably. Although the dictionary definition keeps them separate. So they must mean physical properties and reactions here. So that's what I'm putting there. But basically, the chemical properties, there are different approaches that we can take to learning chemical properties. One is we can memorize patterns, you know, try to memorize like have you heard the AB plus CD pattern? AB plus CD yields what? Well, you just flip them. Or the AX plus B, or the A plus BX pattern. And so we can memorize those patterns. That's one way of understanding chemical reactions, is memorizing them. But that would be kind of the one approach. Another approach is not memorize anything, just mix it. Like if you want to know what happens, if you mix two chemicals together, then mix them together and see what happens, you know? You could do that for everything. That way you don't have to memorize, and you get accurate results because you just see what happens, right? And so that's coming from you know, from observations. And so this is back from Chem 1A. When I think of the scientific method, what do scientists do? Scientists observe nature. They just take observations. They see what happens. You know, will these two chemicals react? Well, we'll mix them together. And then see. And then if you take lots of observations, then we might see patterns. And so this is where the pattern comes from. You know, AB plus CD. AB plus CD's pattern, or A plus BX, or whatever. But what we're trying to do eventually is we're trying to get a deeper understanding of it. Rather than just a simple pattern, we'd like to understand it a little more fundamentally. And so this is patterns or trends. And so this is the way I think of the scientific method. Although the scientific method, you know, a lot of things are discovered serendipitously, like penicillin or whatnot, but even for the discovery of penicillin, if they didn't have a lot of observations, then they wouldn't have understood, you know, how unique that observation was. So pattern, trends, and then we end up with laws. But we want to go a little deeper. You know, the ideal gas law, PV equals nRT. You know, so it's a law. A law is basically a mathematical definition of a pattern. You know, so you have some kind of pattern with gases, and then you come up with a mathematical definition of that, and we call that a law. And for that particular law, we call it an empirical law, you know, or an empirical equation, or, you know what empirical means? Empirical means from observation or based on observation versus theoretical. You know, theoretical would be based on some fundamental theory. So this type of law here from observations would be like the ideal gas law, but you would want to dig deeper, you know. You want to get a better understanding of this. And we could have gotten the ideal gas law from theory as well, because these laws lead to hypotheses. Hypotheses is you're hypothesizing a more fundamental description of what's going on with the gas. You know, why does that gas behave the way it does? And this is a tentative fundamental description. Eventually that leads to a theory. The way scientists define theory is that a theory is something that has widespread acceptance, you know, and that's been tested. And so a lot of people say, well, I'm going to theorize. Like, you might have a theory of if you watch a movie and there's a murderer there, you might have a theory of who the murderer is, you know, whatever. Whereas a hypothesis is just a guess, a tentative kind of thing, initial guess. And so theory, so you might hypothesize the murderer identity. You know, if you get to the theory stage, then most people agree with it. What we're going to do is we're just going to look for patterns in reactivity here in metathesis, acid base, and redox. But what we want to do is we want to do like a two-pronged approach to our understanding of this. When we try to understand these reactions, we're going to try to get a better theoretical understanding of this. In order to get a better theoretical understanding of this, so not everything is just a simple AB plus CD type pattern, and we memorize a whole bunch of those, then what we want to do is to better understand the properties. We want to understand, you know, more fundamentally, what in the composition and what in the structure leads to those particular properties. And so this is trying to gain a more theoretical understanding of this. And so the goal of chemistry is understanding the properties of matter based on what? Because it would be fine if those patterns always led us to the correct answer, but sometimes those patterns don't. And so we need a deeper understanding. So the goal of chemistry is understanding the properties, both physical and chemical, but primarily chemical right now, because that's what we're focusing on, of matter based on composition and structure. And then what we're looking for we're looking for patterns in the composition and structure that lead to those particular properties. So, by looking at composition and structure and how that plays with properties gives us a different route to those versus just observation. In other words, measuring the properties. We can always measure the properties, but we don't want to have to measure everything. It would be nice to be able to predict those properties based on these things. And so this is our two-pronged approach. Coming from here, it's more of a theoretical approach to properties. Coming from here is just experimental, observational approach to properties. Most of the properties are done by measuring, we have books of data. The books of data compile properties of substances, and in fact, Wikipedia is a great example of this. You know, if you go to Wikipedia and look up compounds or elements, you'll see a whole list of properties. Most of those were measured. It's fine measuring, but measuring takes a lot of time and work. So our study is first we're going to look at a whole bunch of observations, and then we'll try to see some patterns in terms of composition structure and chemical reactivity. So this is kind of the slide. I'm skipping some of these slides and go through those. So these are patterns that were based on, let's say, Chem 4. And the patterns that they saw were things like the combination reaction, decomposition reaction, acid-base, single replacement, double replace, combustion, precipitation. How many more are there? It depends on which Chem 4 or Chem 1A instructor you had. In Chem 4, we're required to teach 9 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9. Like metal oxide plus water, non-metal oxide plus water. Those are different patterns that we're supposed to teach in Chem 4. But I particularly like this. I mean, it's kind of nice in one way, but in another way, it's a little bit confusing. So what I do is I group all these into 3 types. And those 3 types are based on driving force. So if I had the combination reaction might have one driving force for one combination reaction, but another combination might be a totally different driving force. So if I look at this one, hydrogen, H2 gas plus oxygen gas. So we'll balance this. We'll need twice as much hydrogen, and this is going to make 2 H2O liquids. L for liquid. There's a G for gas. This is a combination, so we're combining this element and this element. But what if we had something like this? As an example, here. If we took H2O liquid and combined it with CO2 gas to get H2CO3. So this would be combining 2 compounds. And then we have this one, aluminum, actually. Solid. Plus, etc. We'll just say etc. here. And so we have a whole bunch of different combination reactions. So then what we have to do is we have to subdivide the combination reactions depending on the type of combination reaction we have. So this one would be an example of a redox combination reaction. This one would be an example of a Lewis acid base. And then as we go on, we'll have a whole bunch of subcategories of combination reactions to better understand those. And so what I don't want to do is I don't want to get into that. And this is why there are 9 that you had to memorize, but there were actually much more than that if you want to go this route, because there are a whole bunch of subdivisions of this. So what I did was we'll just take a step back. We take a step back, and rather than looking at all the different types of combination reactions that we have, and there are a lot. I'm going to divide it into just 3 types of reactions here. So more examples of this. So this one always confuses students. HCl plus HNO3 plus gold. You know, what do you classify that as? You know, did you learn AB plus CD plus E pattern? Was there? No, there was no AB plus CD plus E, but you should learn it, right? This is a very famous reaction. You know, it's very difficult to dissolve gold. But like hydrochloric acid is not enough. And this acid, what is this acid again? This is a very common acid. Nitric acid's not enough. But a combination of hydrochloric and nitric acid is enough. This is a very interesting reaction. This is called aqua regia. Aqua regia is royal water, and this royal water, don't drink the royal water for sure, it'll kill you. But this is enough to dissolve gold. And why is that? Well, this is very interesting because it's a combination of two. There's a redox reaction here. Nitric acid is what we call an oxidizing acid. It's a very powerful oxidizer. It oxidizes gold, but gold is very difficult to oxidize. And so to push the gold along, we have hydrochloric acid. Hydrochloric acid is not acting as an acid in this reaction. Do you know what hydrochloric acid is acting as? It's acting as a base. Well, how can hydrochloric acid act as a base? How hydrochloric acid acts as a base is because of chloride. Chloride is what we call a Lewis base. Chloride is a ridiculously weak Bronsted base. You know, if you look at the acid-base chart there in the center, you know, chloride is so weak, we consider it neutral. You know. But as a Lewis base, then it's enough. And so this is a combination of redox and acid-base. And we divide it, we write two separate reactions and combine it. And so the first step is the oxidation of gold. The second step is the attack of gold ion with chloride as a Lewis base. Here's an element plus element combination reaction, which is redox. This yields CO2. Here's another example of a combination reaction, although I used a non-metal oxide there. This is metal oxide plus CO2. It's calcium carbonate. So these two reactions are totally different. And so you have to memorize, is it an element plus element combination, or a compound plus compound, or an element plus compound, or et cetera, et cetera. We don't want to do that. And so this first one, we'll just classify it as redox. So it shares a lot of the same characteristics as this redox reaction here. And the second one is Lewis acid base, which shares a lot of characteristics of the Lewis acid base attack reaction here. So it's better to understand the Lewis acid base reactions and the redox reactions than try to combine these. So these three basic types of reactions are based on driving force for reaction. The driving force is, you know, does it precipitate form? Are we going from a stronger acid to weaker acid? The driving forces vary. So for example, metathesis, we have a set of driving forces. Acid-base, we have another set of driving forces. And for redox, we have another set of driving forces that we look at. And the driving forces for redox, you can't apply those to metathesis reactions. And the driving force for redox, you can't apply those to acid-base reactions. It doesn't work. But all metathesis reactions share that. All acid-base reactions share the same driving force, and all redox reactions the same driving force. There are other reactions as well, like photochemical reactions. But photochemical reactions in a lot of ways are like oxidation reduction. And some photochemical reactions are like acid-base, and some are like metathesis. Radicals, you know, but a lot of these are similar, you know. So if you understand these three, then these are easy to understand because it's all the same. It's all like plus and minus, plus charge and minus charge. That's it. And sometimes we have like partial charge, you know, delta plus, delta minus.
that kind of thing. So we'll dig into the driving forces in a little bit more detail. The formation of more thermodynamically stable. This is typically when we think about driving force. You know, there's a driving force for this pen to shoot up to the ceiling. Is there a driving force for the pen to shoot up to the ceiling? If I let go of the pen, will it rise up? No. But if I let go of the pen, what's it going to do? It's going to drop down, and that's because this is higher, what we call potential energy, and down here it's lower. So nature wants to minimize energy, right? That's one of the driving forces. And so this is kind of unstable, you know, precariously perched on my fingertips, and then it fell down. You know? So that's it. Well, what's more thermodynamically stable? What's more thermodynamically stable are things like solids, you know, solids, precipitates, you know, sometimes, or things with stronger bonds, that type of thing. So we have a lot of descriptive ways of looking at that. And so this is what we look at in terms of Chem 1A, you know. And here, I'm just gonna skip some more of these slides here. So we could subdivide these, you know, a lot of these we already know. So for example, in redox, one type of redox reaction is single replacement. And so when we look at the driving force for single replacement, we're going from a more active element, which is thermodynamically less stable, to a less active element, which is thermodynamically stable. So gold is really stable, and therefore its activity is very low. Whereas something like lithium metal is kind of unstable. You know, you got to watch out for fires and that kind of stuff. So lithium is unstable. So that would be a driving force there. But we come up with a general driving force rather than more active element to less active element. We don't have elements all the time. Sometimes we're dealing with compounds. If we're dealing with compounds, then how do we figure that out? And so we come up with a more general statement of what the driving force is, and then we use it for all of these reactions. So we'll just have a general one. And so we have skeleton redox, which is like in chapter 5, and the redox chart method, which is in chapter 20, sort of, etc. For acid base, it's tricky. Acid base has, this is a little bit more difficult because Bronsted-Lowry is easy. All acids and bases are Lewis. And so we only really need one definition of an acid and base, and that would be the Lewis acid base definition. But we primarily use two. Arrhenius we don't really use much at all. We use Bronsted-Lowry and Lewis. Bronsted-Lowry is a small subsection of acids. These are, you know, acids that contain protons and bases that can accept protons. And so Bronsted-Lowry acid-base reactions the driving force is easy. However, we could use the general driving force for all acid-base reactions, which is more difficult. You'd have to know a lot more theoretical knowledge of acids and bases. And so for Lewis acids bases, it's a bit more difficult, and therefore we like to look at this smaller subsection called the Bronsted, and that chart is just for Bronsted there. You know, but all those are also Lewis. But when we're looking at analyzing Bronsted reactions, it's very easy. Lewis reactions, we need a bit more information. Metathesis, you know, the double replacement is just the AD plus CD, but we could have triple replacement, etc. You know, quadruple, you know, doesn't have, or just ions. If we're looking at a net ionic equation, we just see what ions. Metathesis are just ion combinations, favorable ion combinations. So you're just swapping ion partners here to see if you get a more favorable ion combination. And so it doesn't matter how many, quadruple, you know, quintuple, however many compounds you have in there, you're just looking at which ion combinations are the most favorable. And those ion combinations lead to precipitates and weaker acids and that kind of stuff. We'll look at that. When we're doing this, we have to make some basic assumptions. Otherwise, there are too many variables. You know, we don't want too many variables because, you know, those variables will change how our prediction. In Chem 1B, you know, since we're quantifying driving force, we can factor those in. So what happens to the driving force if the temperature goes up? What happens to the driving force if the temperature goes down? What happens to the driving force if the pressure changes? You know, those are the types of things that we want to understand theoretically in Chem 1B. But in Chem 1A, there's too many variables, so we try to have some basic assumptions here to minimize that. And so the concentrations are 1 molar and the gases are 1 atmosphere, or 1 bar. When we see concentrations of 1 molar and gases at 1 atmosphere or 1 bar, what do you think of? Does that sound familiar? It's not STP, it's close. You know, it's often mistaken for STP. STP is standard temperature and pressure, but it's standard temperature and pressure for gases. So standard conditions, we have 2 sets of standard conditions and they're different. So the first set of standard conditions is STP. STP is what, 0 degrees C and?
273
I'll just do this. 0 or 273 Kelvin and? 1 bar. That's STP. We have something called standard thermodynamic conditions. So my first basic assumption is we're under standard thermodynamic conditions. That's it. And so I didn't write standard thermodynamic conditions here because most people don't know what standard thermodynamic conditions are. So if we have a delta H versus a delta H with this little thing up here, what's the little symbol up here? The little circle. Remember that little circle? What does that little circle mean? We have a normal delta H, which can be under any conditions. However, this delta H is restricted to standard thermodynamic conditions. And so what are standard thermodynamic conditions? Standard thermodynamic conditions, which that little superscript represents, standard thermodynamic conditions are the gases at 1 bar or 1 atmosphere, depending, you know, fold. Concentrations are 1 molar. And there's no standard temperature. Because reactions can happen at any temperature. Do all reactions happen at 0 degrees C? In fact, how many reactions do you do at 0 degrees C? Have you ever done a chemical reaction at 0 degrees C? Pour this ice cube into that ice cube and see what happens? Or actually, if you have a solution, probably because of freezing point depression, probably is stale liquid. But there's no standard temperature, but what do you think the most common temperature is?
Room temp.
Yeah, room temp. And room temp is what?
It's like 70.
298 Kelvin. And so if you look at these tables here, look at this footnote here. These potentials are for neutral aqueous solutions. All other E0 values are for 1 molar ion concentrations in gases of 1 atmosphere. This is an old table, so they're still using atmospheres here. now we're switching to bar, and so this would be a 1 bar. So these potentials, we call these oxidation potentials. These oxidation potentials are under standard thermodynamic conditions. Now we need to know what the temperature is. And the temperature for these ones are at 298. They should have said that here, but they're missing it. Because they have to specify the temperature. And our book does it though. Our book specifies the temperature. So if the temperature's not written there, then we're just going to assume they're talking about 298 because 298 Kelvin is the most common temperature that we do reactions at. So that was the chart in our room there. Okay. If we have extremely low, so this 1 molar is, you know, it's not all that concentrated, but it's fairly concentrated. We can have much lower concentrations and we can have higher concentrations than 1 molar. But not too much higher. I mean, we aren't going to get 100 molar, 1,000 molar. 1,000 molar would be way too much to pack in a liter, you know. Like, if I had a liter, you know, pure water, how many moles of water can you fit in a liter? Do you know how many moles of water you can fit in a liter? 55.5, a little less than 55.5 moles of water can fit in a liter. So the maximum concentration of water is going to be 55.5. That would be pure water, 100%. But we can go the other extreme. Extremely low or extremely high concentrations may require compensating for. So we could get, for example, here, if we have very low concentrations, you know, we expect this AD plus CD reaction to occur. This is hydrochloric acid plus nitric acid. So the AD plus CD yields AD plus CB. And silver chloride is a precipitate. And so we expect precipitation to occur. That's a driving force. Precipitates are usually stable. However, if we have very dilute concentrations of HCl and silver nitrate, nothing happens. You know, we don't get any precipitate. That's extremely dilute concentration. So you might mix them together and nothing happens, even though you predict a precipitate here. That's because we aren't, you know, working at standard thermodynamic conditions. Likewise here, this would be silver chloride salt plus 1 molar nitric acid. Well, 1 molar nitric acid isn't enough, and so we get no reaction here. But if you take silver chloride and you use concentrated nitric, you might get a little bit of reaction, but if you use hot concentrated nitric acid, then you'll get a reaction. But you aren't going to get the reaction that you expect. You know, what's going to happen is you're going to generate some chlorine gas and some other stuff. It'll be a nasty, toxic mix or product here with fuming orange clouds of smoke coming from this. But this is one way to dissolve it. And so you go non-standard thermodynamic conditions and you see what happens. You know, and these are observations, but it would be nice to be able to predict, you know. It would be nice to predict what should happen, you know, if we change the temperature, change the concentrations. Obviously, we can observe it, you know. You can just take observations. You know, how hot does a hot concentrated nitric acid need to be? What is the minimum concentration, you know, in order to get this to go? Correct the mistake here. Yeah, and then there are other things that could happen. Like here, if you do this stoichiometrically, we should get lead 2 hydroxide precipitate. However, if you add excess sodium hydroxide, then all the precipitate disappears. So this is a weird reaction because initially you get a white precipitate grows and grows and you're trying to get more and more precipitate. Usually we try to maximize the amount of precipitate we get. So you keep adding more sodium hydroxide, and then you go, okay, if 1 milliliter is good, then 10 milliliters is even better. So you just keep adding more and more sodium hydroxide and then all of a sudden it disappears. Like you add a drop and it starts to fade. And you add another drop and it's gone and it vanishes. It's like a magic trick. The precipitate disappeared. And so this disappearing precipitate is, you know, some side reaction. This is actually a Lewis acid-base reaction occurs. And the Lewis acid-base reaction attacks the precipitate to form this. This is what we call a transition metal complex. And so we want to understand cases where this might happen. And so the precipitate gets attacked by excess hydroxide and we form this. So this is called hydroxo plumbate 2 ion and sodium nitrate. Okay, the other thing we're looking at is we're looking at the thermodynamic driving force. And so to properly predict the reactions, we must understand the kinetics. You know, this is what I talked about earlier. Diamonds are essentially forever, but there is a driving force here. You know, diamonds would be higher in potential energy, graphite's lower in potential energy, so it should fall down, but it doesn't. And so we call that metastable. You know, the graphite's not. Graphite is more thermodynamically stable, but diamond's not going anywhere. We'll talk about that more theoretically later. So the first type of reaction we're going to cover is metathesis. Metathesis would be just the ion combinations. The goal of which is to find favorable ion combinations. What is a favorable ion combination? A favorable ion combination yields a precipitate. A favorable ion combination yields gas. A favorable ion combination yields a weaker acid from a stronger acid, or a weaker base from a stronger base. Usually it's easier just to look at the acid, because if it's a, you know, okay, so those are favorable ion combinations. However, some things aren't ions. Like, for example, weak electrolytes. Weak electrolytes are molecular compounds that react with water to form some ions. So, for example, ammonia is what we call a weak base. Weak bases are weak electrolytes. Weak electrolytes partially, what we say, hydrolyze water. And so ammonia reacts with water to form a little bit of ammonium and hydroxide. Well, the ammonium and hydroxide can undergo metathesis reactions. Even though ammonia itself is not an ion, it reacts to form some ions, not much, but a little bit. And we have a whole bunch of these ammonia-like compounds. These ammonia-like compounds are called amines. And those amines behave just like ammonia because structurally they have the same characteristics as ammonia, characteristic properties as ammonia. So, you know, the two different approaches that we're looking at would be like this. This is ammonia with Lewis structure. And these ammonia-like compounds would be something like this. This is called methylamine. And I expect methylamine to behave very similarly to ammonia. And because chemistry is dealing with electrical forces, then what's important is understanding how the electron cloud is distributed here. And so what's more electronegative, hydrogen or nitrogen? Hydrogen has electronegativity of like 2.1. Whereas, this is the way I remember, fluorine has the highest electronegativity. What is it? What's the highest electronegativity on the Pauling's electronegativity table? 4.0. And then I just drop it by half. So if I go fluorine, oxygen would be a 3.5, nitrogen should be a 3.0. And so which one is more electronegative? Nitrogen's more electronegative. It's a 3.0 versus a 2.1. Okay? And so what that's going to do is it's going to suck in the electron cloud towards it. And that's going to make this delta minus. Delta minus. It's a weak base. Acids are H plus. And so we see, we want the nitrogen to be negative, then it can attract an H plus. This is also a weak base. But over here, hydrogen's a 2,1, but now we have a carbon here. But what is the carbon's electronegativity? The carbon's electronegativity is a 2.5. And so 2.5 is bigger than 2.1. It's 0.4 bigger. But is 0.4 very significant as far as electronegativity difference? It turns out, no. I mean, a 2.1 and 2.5, these are very close. Similar. You know. In fact, when hydrogen is bonded to carbon, we call it non-polar. So if we have a 2.1 versus a 2.5, the difference in electronegativity is only 0.4. 0.4 difference in electronegativity, we call it a non-polar bond. That is, it's not really polarized. And so 2.5 and 2.1 are close. And we have hydrocarbons, which are all non-polar. So this does not change the delta minus. The delta minus here would shrink a little bit because carbon is slightly more, but it's not going to shrink that much. Like that. But there are other factors here, which we're going to talk about more later. We'll talk about this more later. Even though you think that shrinks a little bit, it turns out that this one is a better base than that one. This one's a better base than that one because this carbon is what we call electron rich. When you look at that carbon, does that look electron rich to you? And what do I mean by electron rich? Because I don't see a lot of electrons here. I see the electrons in the bonds here. But it turns out that this base is stronger. Both of these are weak. And they're very close in strength. But this one turns out to be a little bit stronger. Why is that? Well, it's not because of this, because this delta minus should be a little bit smaller, but it's because of this carbon here. The carbon is what we term electron rich, and so this is getting more theoretical understanding. One, you could just memorize it. You can just memorize, okay, this methylamine is a stronger base than ammonia. Or two, you can try to understand some theory so we don't have to memorize things because we can't memorize everything. I mean, there's just too much stuff to memorize. So if I had dimethylamine would be two methyls on the amine. Would that be an even stronger base or a weaker base? Well, one, we could just look it up, memorize it, or two, we can try to figure out theoretically. And theoretically, yeah, you'd expect it to be a stronger base than methylamine. And so the more theoretical understanding of these things, the better, because then we'll try to minimize the amount of memorization or looking up that we have to do. And so, so what I mean by this, you know, these occur in metathesis. In terms of metathesis, ammonia is not an ion, but ammonia reacts with water. And this is not favorable to form ammonium and hydroxide. So I'm going to write two arrows here. The forward arrow, you know, is not the favored direction. The reverse arrow is bigger. That's our downhill direction. And so this reaction is going uphill in terms of energy and stability. However, it's not so far uphill that nothing happened. You know? And so a small population, this means a small population of ammonia and water can make it to the top of the hill. Whereas if we're at the top of the hill, everybody can make it down. Well, methylamine is the same thing. Methylamine, which would be CH3NH2 plus water, will form a small amount of ions. The first ion it's going to form is methyl ammonium ion and hydroxide. The positive charge here is actually on the nitrogen here, so I can throw it there, or I can throw out the positive charge out here, however you want to do it. But typically, I don't know, to make it more. And the same thing in ammonium, the positive charge is on the nitrogen. You know, ammonium has 4 hydrogens on it, and the positive charge there. If we take off one of the hydrogens and replace it with methyl, then we have methyl ammonium ion. And so this is called methyl ammonium, this is called methylamine, this is called methyl ammonium. This is called ammonia, that's called ammonium. We have a whole bunch of amines, thousands and thousands of amines. I'm sorry? We're out of time? Okay. Thanks.